Welcome to Selection Sathi. Today we tackle dynamic programming, arguably the most important algorithmic technique for gate and coding interviews. DP transforms exponential time brute force solutions into polynomial time ones by avoiding redundant computation. We will cover the two key properties, memoization versus tabulation, and solve classic problems step by step. The first property of DP is overlapping subproblems. In naive recursion, the same subproblem gets computed again and again. Take Fibonacci. To compute f of 5, you need f of 4 and f of 3. But f of 4 also needs f of 3, and f of 3 needs f of 2, which appears multiple times. Without DP, the recursion tree has exponential nodes, O of 2 to the n. DP stores the result of each subproblem when first computed. Next time the same subproblem appears, we just look it up, no recomputation. This brings Fibonacci down from exponential to O of n. The second property is optimal substructure. A problem has optimal substructure if its optimal solution can be constructed from optimal solutions to its subproblems. Shortest path is a classic example. The shortest path from A to C through B uses the shortest path from A to B and the shortest path from B to C. In the knapsack problem, the best value for capacity W combines the best choice for the current item with the best solution for the remaining capacity. If a problem lacks optimal substructure, DP cannot be applied. For instance, the longest simple path problem does not have this property. There are two approaches to implement DP, top-down and bottom-up. Top-down, also called memoization, starts with the original problem and recursively breaks it down. A cache stores results of solved subproblems. It is easy to implement, just add a dictionary to your recursive function. Bottom-up, or tabulation, fills a table iteratively from the smallest subproblem upward. It avoids recursion overhead and stack overflow risks. In practice, tabulation is usually faster. Both give the same time complexity, but space can sometimes be optimized in bottom-up. The key to solving any DP problem is defining the state and writing the transition. The state is the information that uniquely identifies a subproblem, for example, the current index and remaining capacity in knapsack. The transition is the recurrence relation, how you compute the answer for a state from previously solved states. The base case is the simplest subproblem with a known answer. Follow these 4 steps, define the state, write the recurrence, set the base cases, and determine the order of computation. Let us compute Fibonacci of 6 with memoization. Naively, f of 6 calls f of 5 and f of 4. F of 5 calls f of 4 and f of 3. Notice f of 4 is already being computed above. The naive tree has 25 total calls with massive duplication. With memoization, when f of 5 needs f of 4, it finds it already in the cache. Similarly, f of 3 is cached, f of 2 is cached. We only compute 7 unique values, f of 0 through f of 6. F of 6 equals 8, computed in O of n time and O of n space. The 0-1 knapsack problem. 3 items with weights 1, 2, 3 and values 6, 10, 12. Capacity is 5. State dp of I, W equals the maximum value using the first I items with capacity W transition. For each item, either skip it and keep dp of I minus 1, W, or take it and add its value to dp of I minus 1, w minus weight I, fill the table row by row. At dp of 3, 5 we get 22, which is achieved by taking item 2 and item 3 with total weight 5 and total value 22. Longest common subsequence of ABDAB and BDCAB. State dp of I, j is the LCS length of the first I characters of string 1 and the first j characters of string 2. Transition, if the characters match, dp of I, j equals dp of I minus 1, j minus 1 plus 1. If they do not match, take the maximum of dp of I minus 1, j and dp of I, j minus 1. We fill a 7 by 5 table. The answer at dp of 7, 5 is 4. Backtracking from the bottom right corner gives us the subsequence B, C, A, B. Coin change problem. Coins are 1, 3, and 4. Make amount 6 with minimum coins. State dp of I is the minimum number of coins to make amount I. Base case, dp of 0 equals 0. All others start at infinity. dp of 1 equals 1 using con 1. dp of 2 equals 2. dp of 3 equals 1 using con 3 directly. dp of 4 equals 1 using con 4. dp of 5 equals 2, con 1 plus con 4. dp of 6 equals 2, using 2 cons of 3. Notice the greedy approach would pick 4 then 1, giving 3 cons. dp finds the optimal answer of 2 cons. Quick exam tips. First, check both properties, overlapping subproblems and optimal substructure. Second, start with the recursive solution and add memoization, easiest way to get started. Third, gate often asks for the recurrence or the table dimensions, so focus on state definition. Fourth, if dp of I only depends on dp of I minus 1, use 2 rows instead of the full table to save space. For more concept videos like this, download the Selection Sathi app. Like and subscribe. Thank you.